Okay, in today's lesson, number 2 in Chapter 8, we're going to cover bond energies 8.8, Lewis structures 8.10, exceptions to the octet rule 8.11, and resonance 8.12. So each type of bond has a certain amount of energy associated with it. And you know that when we break bonds, we have to absorb energy, and when we make bonds, we release energy. In my book, this is on page 374. It's probably going to be around the same place, but maybe not exactly the same page in your book. And in order to do problems where you have to calculate the overall energy involved in a reaction, you need to use this table. One thing that I do want to draw your attention to is that in carbon dioxide, the CO double bond has a special energy value, which is 799, which differs from the regular CO bond energy of 745. So please pay attention to that if you're dealing with CO2 in a molecule. All right, let's do some practice problems with this. So we need to calculate delta H for the reaction that you see here. Now, one thing that you have to remember is there's been different places where we've calculated delta H before. We've calculated delta H when we use the heat of formation table, which is when we form 1 mole of a substance. And recall that that is always the sum of the products minus the sum of the reactants. And in another example with Hess's law, we had to manipulate reactions, either double them, reverse them, halve them, in order to come out with the final reaction, because a reaction happens in a series of steps. And in that case, we were summing the delta H's of the subsequent reactions. So finally, in bond energies, which is what this section is all about, we're going to do bonds broken minus bonds formed. So I just want to review that. So this is going to be the sum of bonds broken minus the sum of bonds formed. And I know I said that in the previous lesson, but we didn't get to do any sample problems. I find the easiest way when you're starting out to do these problems is to actually draw them. So what I do is I want to make sure I don't miss any bonds. So when I look at CH4, I know that it's C with 4 H's around it. Plus, I have 2 Cl2s. So I've got Cl, Cl, and Cl, Cl. I also have 2 F2s. So FF, FF. And I'm not telling you that you have to do this. I'm just using it as a learning point so that you can see what's happening. And then we have CF2, Cl2. It doesn't really matter which side goes where, because we are using one dimension to draw a three-dimensional object. We have 2 HFs, and 2 HCl's. And I'll show you why I did that. Okay, that's because my arrow didn't want to get put in here. So now we have to look at the bond energies that are associated with these. And the reason why I drew them out is because I want to make sure that you don't short any of the bonds. So remember, we're starting with bonds broken. Right? So this is your bonds broken side minus bonds formed. All right, so let's start over here. We have CH4, and in that we have 4 CH bonds. So what I'm going to do is I'm going to go up to my chart. I'm just going to do this once. I'm going to find CH. I see that CH is 413. Okay, so I'm going to come back down here, and I've got 4 times 413 because there's 4 CH bonds. Plus, I have 2 Cl-Cl bonds, and Cl is 239. And I have 2 FF bonds, and F is 154. And that's going to be minus my bonds formed. Over here I have CF2, Cl2. So within that molecule I have 2 CF bonds, and I have 2 Cl bonds, which is 339, plus I have 2 HF bonds, which is 565, plus I have 2 HCl bonds, 427. So I have a total here of 2438 minus my total here of 3632. So I get a grand total of 1,194 kilojoules. Negative. Make sure I got that negative sign in there. So what that tells us when we're looking at the reaction is that although bonds have been broken and new bonds formed, the overall reaction is exothermic. All right, let's look at another one. So this one's a little more challenging in the sense that the drawing of the molecules is complicated, and you wouldn't get one like this on the exam. And we haven't talked about drawing Lewis structures yet, so don't worry about that. So what you have is 5N2O4. So how we would draw N2O4 is like this. We would have N, N, and we have 5 of these. Okay, so we've got 2 double bonds and we have 2 single bonds. So the O's with the single bonds have 6 valence electrons. The O with the double bonds have the 4 electrons around it. Plus, we have N2H3CH3. So we've got N2, so we've got 2 N's bonded to one another, and that's bonded to a C that has 3 H's around it. And then we have 3 hydrogens around the ends. So we have 2 coming off the N, 1 here, and a lone pair. Like I said, I'm doing this for the practical sense of showing you how to do these problems. And we have 4 of those. And that's going to yield 12 waters. Everyone should remember how to draw water. Plus 9 nitrogens Well, that's going to be a triple bond. Plus 4 CO2. All right, so let's break this down as far as values. I'm going to list, because this one's really complicated, underneath what I have. If you don't want to do this part, that's fine. You can wait till I get right to the numbers. So when I look at this first molecule, I see that I've got 2 N-double-O bonds, right? I also see that I've got an N-N bond, and I also see that I've got 2 NO bonds. So that's basically what I'm going to write down here. I have 5 times 2, and I have N-double-O bonds. I also have 5 times 2 NO bonds. And I have 5 NN bonds. Next I have 3 NH bonds. I also have 3 CH bonds. I also have an NN bond, and I have an NC bond. Okay, so let's write that all down below. 4 times 3 NH bonds. I have 4 times 3 CH bonds. I have 4 times 1 of an NN bond and 4 times 1 of an NC bond. Then I go to my water, okay, and I have 12 times 2 HO bonds plus 9 N triple bonds plus 4 times 2 C-double-O bonds. Okay, let's do the math on this. Okay, so we have, starting from the bottom up, we have 5 times 160, that's the NN bond, plus we have 10 times 201, which is the NO single bond, plus we have 10 times 607, which is the N-double-O bond. In the next molecule, we have 4 NC bonds at 305 plus 4 NN bonds at 160 plus 12 CH bonds at 413 and 12 NH bonds at 391. Okay. Then we have to subtract the bonds broken. So I'm going to do that right over here. We have 12 times 2, which is 24 HO bonds at 467, plus we have 9 triple N bonds at 941, plus we have 4 times 2, we have 8 C-double-O bonds, and that's specifically in the carbon dioxide, which is going to be 799. So when we do the math on all of this, I get $880 for this first set of brackets, 8,880 for this set of brackets. And then over here, for the second set of brackets, I get 11,508. So when I add the two of them together, I get $20,308, and then our bonds formed came out to 26,069. So bonds broken minus bonds formed came up with a grand total of negative 5,681 kilojoules. Now, you will never see a problem like this, I promise you. More realistically, you'll see one like in example 1. Just wanted to show you how you really go about paying close attention to the types of bonds you have, the number of bonds you have, double checking your math, so on and so forth. Now, this bottom example, example 3, I'm going to talk about this one in class on Monday. This is also a little bit of a bear of a problem, and you might have to do part of it, but certainly not the whole thing. So this is going to end this lesson, and you need to watch the next lesson as well, which is going to be on Lewis structures, formal charge, and resonance. And then you'll be able to do the problem set. So this lesson is on Chapter 10, and it's kind of weird because we talk about Chapter 10 after we talk about Chapter 8 and 9, which is bonding and molecular geometry, and we kind of talked about some of these things as we were going through it. So this is going to put everything all together. We're going to start with intermolecular forces, and to do that we need to review bonding, which we just spent 2 chapters on. So as you know, bonding, there's 3 major types: covalent, ionic, and metallic. And you know that covalent is between non-metals, and ionic is between a metal and a non-metal, and metallic is between 2 metals. Then when we look at covalent, we can break that down into polar and non-polar. And we have our LDFs, which is our London dispersion forces, which is actually our weakest. And then we have hydrogen bonding, and this is when hydrogen bonds with NOF, nitrogen, oxygen, or fluorine, which we're going to actually talk about in a minute. And then we have dipole forces, which is basically everything else that is polar that is not hydrogen bonding. So when we talk about strength, we want to talk about strongest to weakest. So hydrogen would be the strongest out of these three, and then dipole, and then nonpolar would be the weakest. Now, overarching, when we talk about all of the bonds, just to review, we have that saying, never imagine me having dirty napkins. So we have never imagine me having dirty napkins. And this stands for network, ionic, metallic, hydrogen, dipole, and nonpolar. So when we think about it, this is actually the strength. This is going to be from strongest to weakest. And in there you can see that when we talk about specifically covalent bonding, we have hydrogen, dipole, and nonpolar, which is the order that I just reviewed down here. So let's look at a dipole sketch using HCl. You know that H bonds to Cl, and you know that there's a dipole moment. And that dipole moment is in the direction of Cl, because Cl has a higher electronegativity. So remember that the head of the arrow always points toward the more electronegative element, the tail toward the positive. It forms that positive sign. And then you can actually mark it if you want, positive, negative. Now, if I were to have another HCl in here, same thing's going to happen. We still have that dipole moment, but now we have what's called a dipole force, and that is between the Cl and the H. This is our dipole force. And it's the electrostatic force that holds the two molecules together. So just remember here, hydrogen bonding, here's another way. I say NOF. Other people say, what does ET say? ET says phone, home. So you've got the H with the NOF, nitrogen, oxygen, fluorine. So it's just another way to remember it. So let's look at a hydrogen bond sketch using water. We know that water is a bent molecule due to the two lone pairs of electrons on it. Therefore, we know that the dipole moment is in the upward direction. So this side of the water molecule is slightly negative, this side is slightly positive. Now if we get another water molecule in close proximity of this, again, we also have another dipole moment. This side slightly negative, this side slightly positive. And then we have the hydrogen bond, which is this right here. This is considered the hydrogen bond between the two water molecules. All right. In this next picture, and I apologize that it only shows up in black and white on yours, because it's hard for you to see the difference between the attractive forces and the repulsions. The attraction actually is in red, and everything looks in one color on yours, and that's going to be between the positive and the negative. So between the positive and the negative. So here, right here, you have an attractive force. This is also an attractive force. This over here, though, inside, this would be a repulsive force. And the same thing right here, that one. So when you have like charges, you have repulsive forces. Opposite charges, you have attractive forces. So this shows you a dipole force in A here, and that's like representing the HCl that we just did. Down below here, I just drew water for you, but you can also see water. So between the H bonds are represented by the blue dots that you see. These are your H bonds. And then remember, the H bonded to the O is your covalent bond. So this here, this HO is a covalent bond because it's within the molecule. These are hydrogen bonds that are that's why they're called intramolecular forces, because they are between molecules. So in this case, between molecules of water. And what we want to look at on this last diagram here is it's showing you that your H bonds, the boiling point is very, very high. So here's the boiling point of water, 100 HF and NH3. So without hydrogen bonding, life would not be possible on Earth. Remember that the bigger the size, the higher the boiling point. So that's a direct relationship. So let's talk about London dispersion forces. We know that London dispersion forces occur in nonpolar molecules. And these are forces that exist among nonpolar molecules. But it's due to the creating of an instantaneous dipole, which induces another dipole temporarily in a neighboring molecule. And that's because electrons are not evenly distributed, and we don't know where an electron is in every instance of time. So let's look at the oxygen molecule. So you've got oxygen, and it's got two lone pairs of electrons. And remember that these electrons are constantly moving, constantly moving. So what happens is that because the electrons are constantly moving, there might be instantaneously where one side is slightly more positive and the other one is slightly more negative. I put the S for slight. And then what happens is that that gets close to another molecule, in which case one side of that molecule might be slightly positive and the other slightly negative. So you wind up with this very, very weak force between the oxygen molecules. So this is where your London dispersion force is, and this is a very weak force between the outer lone pairs of electrons. So which molecules exhibit London dispersion forces? Well, technically all of them. But when we talk about what force is present in a molecule, we talk about the most prevalent force. So although water has a dipole force, it predominantly, the water molecules have hydrogen bonds between them. When we talk about molecules, they all have LDF forces, but the prevalent force of LDF is in nonpolar molecules. So we always want to talk about which force is the most prevalent. So that constant motion of the electrons, remember, creates a momentary dipole, which continually will happen over and over again, creating these LDFs. So this is actually the best way to try to explain in pictures what I just did. On the left side, you have the electron cloud model, and on the right, you just have using an example with actual atoms. So you have hydrogen, H2, and you have molecule A and molecule B on the right here with no polarization. And then what happens, because of the electrons being continually in random motion, molecule A winds up with an instantaneous dipole. So one side is slightly negative, one side slightly positive, just because there might be more electrons on one side of the molecule at that instantaneous moment. So more electrons means more negative charge on that side, which means the other side is more positive. Well, when that happens, that induces an instantaneous dipole in molecule B. Now you've got the positive and the negative next to each other, and you wind up with the LDF force right here in between them. All right, and then on the left, it's showing you the same thing with the electron cloud. So the bigger the molecule, the more electrons it has. And the more polarizable it is. And no, I didn't make that word up. And that means the higher the boiling point, which I already told you. And you can see that here, okay? So helium, negative 269.7, and then as you get to the bigger molecules, argon, krypton, xenon. Okay, the higher, sorry, the freezing point, which is in direct relation to the boiling point. I thought this was the boiling point chart. Another thing that I do want to point out is that sometimes you will see LDFs are also referred to as van der Waals, AA, two A's. Forces. Okay, so let's take a look at these two molecules. We have 2,2-dimethylpropane with a boiling point of 95 degrees. And then we have pentane with a boiling point of 35 degrees. So this molecule is C5H12. And this one is also C5H12. So look here, okay, just changing the shape of the molecule, remember, you're creating an isomer, changes its physical and chemical properties. So as you see here, 2,2-dimethylpropane has a lower boiling point than pentane. And that's basically because of its structure. The long chain like this on the pentane on the right is stronger, and it's going to take more energy to split it apart. Remember, big molecules have lots of London dispersion forces, and especially nonpolar molecules, that makes them immiscible in water because water is polar. Also, liquids, you have to remember, have properties of beating or surface tension or capillary action. And stronger intermolecular forces causes each of those to increase, which is also going to affect the boiling point. All right, let's take a quick look at metallic bonding. The key player in metallic bonding, obviously, is the valence electrons. Defining property of metals. There's a word missing. It should be is the conductivity of electrons and heat. Remember that we say that metals are positive ions in a sea of mobile electrons. So you have your positive metal ions, could be silver, gold, copper, whatever it is, and you have your negative charges, and they're constantly moving. And what happens is that eventually one side, because they're constantly moving, winds up with a slightly negative charge and the other side a slightly positive charge. And that's due to the sea of moving electrons. And that's basically that is the explanation for what's happening there. Okay, and here's actually a nice picture, probably nicer than the one that I drew, of exactly what I just told you. So you've got your metal ions, the electrons are constantly moving, and one side becomes more slightly positive and the other is going to become more slightly negative. So we're going to move on now to something that is new to this unit, and, well, not, the concept isn't new, but we're going to talk about something new related to the concept, and that's an alloy, which is a mixture of elements with metallic properties. So basically this is a mixture of metals. So in the top example, so we're going to first talk about a substitutional alloy. And here you have copper and zinc. So that actually makes brass, copper and zinc. And what happens is you remove basically 1/3 of the copper atoms and replace it with a zinc atom. So you take copper out and you put zinc in. And this is called a substitutional alloy. Another example of a substitutional alloy is something called Plumbers Solder, which is 95% tin and 5% antimony. Another example, sterling silver, is 93% silver and about 7% copper, which I'm sure many of you probably didn't even realize. But why does it do that? Because silver on its own would be very, very malleable. It would be very easy to bend. The copper, even though it's only 7%, adds strength and stability to the alloy. Now, the other kind we have is what's called an interstitial alloy. And an example of this is iron and carbon, which makes steel. And what happens is the spaces between the tightly packed structure are filled with smaller atoms. So those small spaces between the iron atoms are stuffed with carbon. And the reason why it's malleable is because of the holes in between the different atoms. The best explanation that I can give you is for why alloys become hard and strong like steel is because when you put that carbon in the spaces between the iron, the carbons form directional bonds, and those directional bonds stabilizes and makes the alloy extremely strong. Okay, so moving on to, I said why they were malleable before, and that was because of the spaces in between them. Network solids, molecules with all covalent bonds. Only compounds that contain carbon and silicon. So some examples, SiO2. Carbon, we have diamonds. This is sand. We have diamonds. We also have graphite. All right, so let's take a look at some of these. So here we have diamond, which is very, very strong, and that's because each carbon in diamond, you know, is surrounded by a tetrahedral arrangement of other carbon atoms. So covalent bonds formed between the carbon atoms with the tetrahedral arrangement. Remember, each carbon atom is sp3 hybridized, so those sp3 hybridized atomic orbitals overlap and they form an interlocking network. In the one below, you have graphite. And here, the difference is it's still carbon, but it's the way that it's arranged. It's these are LDFs, and the reason why they're very weak is because they're arranged in sheets. The carbons are arranged in sheets, and then the sheets connect through LDF bonds. Down below is another example of it. Here you can see the 6-member carbon rings fused together. Now, as I said, SiO2 is sand, but it goes by its empirical formula. And sand is based on a network of SiO4 tetrahedrals. So let me explain this a little bit differently. Silicon, oxygen compounds, are often referred to as silica. You might be more familiar with it from earth science as in the terminology of silicates, which are found in like a lot of rocks, soils, and clay. But they're also based on the SiO4 interconnected tetrahedra. But the ratio of the OS relationship is greater than 2 to 1, whereas in sand, which is quartz, it is 2 to 1. All right. These are just some examples of some silicate anions. But remember, they're all based on the SiO4. Okay. You're not going to be tested on this. You do need to know that SiO2 is quartz. It's a network solid. It's got, one of the strongest bonds, high melting point, that kind of stuff. So these molecular solids here are characterized by strong covalent bonding within the molecule. But weak forces between the molecules. So this includes certain forms of sulfur, carbon dioxide, solid, meaning dry ice, because we're talking about molecular solids, and O2 solid. And the reason for this varying forces that exist among the molecules in a molecular solid depends on the nature of the molecules. Many molecules, such as CO2, I2, P4, S8, they have no dipole moment. And the intermolecular forces are London dispersion forces. And if you look at page 479 in your textbook, this has to do with the a comparison of the interatomic and intermolecular distances in the solids that we're talking about here. And that table is on page 479. Again, that's not something you're going to be tested on, but I just did want to mention it. And this last page is just a really nice table that sums up the different types of solids and the bonds and their properties and some examples. And that's it.